Perfect. All right, welcome to the final review session. For those of you watching the recording, I'm very glad you're here to join us. We just drank a lot of water and we had a little bit of a Bible study. And this was a very, very moving moment for us. And it's a perfect segue as we move on to organic chemistry. All right. So we're going to move on. What is that, number 3? Okay, that's for later. Oh, shit. Okay, we got it. We got it. Okay. We're dealing with naming. Some things that a lot of people were functionally fixed on was what if you had like a weird alkyl chain on a benzene ring? And you might be really, really inclined. Let me make sure I'm recording. Good. You might be really, really inclined to make your naming based off of the benzene ring. But in most occasions, the benzene ring is actually going to be a branch, being a phenyl group. Now, if there's a CH2 between the benzene ring and the alkyl chain, you're actually going to have a benzyl group. Remember, make sure you know the difference between a phenyl and a benzyl group. There's a CH2 in the benzyl group, which kind of seems counterintuitive because if a benzyl group has a CH2, wouldn't it just make more sense for the benzyl group to just be the straight up benzene ring? Which you're right in assuming or questioning that, but this is organic chemistry and IUPAC hates you guys. That has been a very common trend. You can quote me on that. But most of the time it's going to be a branch group. Now, if you have, again, just an alkyl chain, it's going to take priority. But if you don't have an alkyl chain like you do here, and they're just common benzene rings, then you just name it following your benzene rules. Now here I see a benzene ring, but right now I also see a very complicated alkyl chain right here, right? For that alkyl chain, I might be thinking, well, would it be like a excuse me, 2-hydroxy penten 2 or 4-hydroxy penten 2-il something. That should be no. It's not going to be branch over branch because we want to minimize the branch over branch, and we would rather just look at the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We want to prioritize the alkyl chain. Now, what takes priority? A benzene ring or a hydroxy? The answer would be a hydroxy. So we would go with the red numbering, and we would have a 4 phenyl. You know, you think, well, we just talked about the hydroxy. Why doesn't the hydroxy come first? Well, remember, if hydroxy is taking the priority, it's actually going to be a pentanol. Pentan to all. Perfect. Now we don't have an alkyl chain. We just have a straight up benzene ring. So now we have to look at a priority chart. Our priority chart, we should know the highest priority is going to be a carboxylic acid. So if benzoic acid is going to be our parent chain, then let me make a note, benzoic acid. Benzoic acid, we look at our branches, and there's only one other branch, an amino group, and that makes it really easy for us. Going from 1, 2, our priority taking the first carbon, to amino, benzoic acid. Benzoic acid. Remember, benzoic acid is one of the names where you actually have a space. Make sure you make note of that. Now take a look at this. We have a chlorine, nitro, and a bromo group. If we were to go chloro, nitro, bromine, it would be 1, 2, 3. And on the other way, it would be 1, 2, 3. All right. And I know I have to start at one of the ends because we start at the point of difference. If we started at chlorine or bromine, we would maximize or actually minimize the numbers used. Let me turn it this way. That might be better for you guys. Yeah. Minimize the numbers used. So if that's the case, well, which one takes priority? Well, in terms of priority, well, if there's a tiebreaker, we use alphabetical order. So it would actually be the red numbering once again. It would be 1 bromo. Oh, shit. 1 bromo, 3 chloro, 2 nitro, benzene. There is no priority group. There is no like common names like benzoic acid, aniline, um, aniline, phenol, all that stuff. All right, now let's take a look here. We have 2 chloros, a nitro, and not a nitro, an amine, and a bromo group. Which one takes priority? They might be inclined to either pick the top or the bottom, right? We have the greatest pointed or the least pointed difference, and you're minimizing the numbers used this way or this way. But we actually do have a priority group this time. That's going to be an amino group. And if we have an amino group on a benzene ring, that's going to be an aniline. So I know that this must be our number one carbon in aniline. Now, to determine, okay, which way do we go? Do we go this way or this way? Maybe thinking, well, okay, if I have bromine and a chlorine, the bromine takes priority. No. Alphabetical order only takes priority as a tiebreaker. And right here, there is no tie. You would get a 2, 3, 6, right? 2, 3, 6 over here. But if you go the other way, it'll be 2, 5, 6. 2, 3, 6 versus 2, 2, 3, 6 versus 2, 5, 6. 2, 3, 6 wins. So we would go counterclockwise. It would be 1, 2, 3, 4, 5, 6. So our answer would be 6 bromo, 2, 3, dichloroaniline. Perfect. All right. Well, whoop-de-doo, we have 2 priority groups. Which one takes priority? Phenol. Same deal as we had back in semester 1, alcohols take priority over amines. So phenol is going to be our priority group, phenol. We know that is going to be carbon number 1. Thankfully, there's only one direction we can go, 2. Great. So it's going to be just 2 amino, phenol. Oh, and now here's a real doozy. We have pyridine. Pyridine, well, where do you start, right? Which one takes priority? Well, when you have a heterocycle, the heteroatom is going to be your first carbon, right? Your heteroatom. So if this is carbon 1 and this is carbon 2, this is just going to be 2-methyl pyridine. Excuse me. Hopefully you guys can recognize your great and valuable aromatic compounds. Very, very important in biochemistry. Pyridine, if you added another nitrogen on it, it would be pyrimidine, which can be further synthesized into thymine, cytosine, and uracil. Come on, get in there. Yeah, uracil. I think it is what? I think thymine is the one that's the something methyl uracil. I think. I'm pretty sure. I think thymine and uracil have like a 1-methyl difference. I think that's what it is. Man, what a nerd am I. What a tough cookie. And now we look at the common names. Now, these common names, I shouldn't really explain to you. These are just all in the Quizlet, and you should know just for memorization's sake. This is going to be a parole. This is going to be a very, very handy structure. If you look at, I think it was indole, where there's another nitrogen on it, that's going to be the side chain. No, it's going to be imidazole, not indole. Imidazole is going to have the side chain that's associated with histidine. All right, and then this is going to be isoquinoline. If the nitrogen was over here, we all know that this would be quinoline. And this is going to be xylene. Here, let me make that a little better. Xylene. 2 methyl groups, xylene. And we can be a little bit more specific. Not we can, we will be a little more specific. This is going to be metaxylene. These are going to be meta to each other. Now, he's a real doozy. Which of the following are going to be aromatic? I have an entire video on aromaticity. An entire video. If you haven't seen it, please go see it. But we know for definitions for aromatic, we need to be planar, Huckel number, continuous, cyclic. And these usually go hand in hand. Continuous and cyclic. So let's look at the first one. First off, it is cyclic. It is continuous. Now let's look at the Huckel numbers, right? This is the main point where he'll probably try to test you on this. So right now I see 2, 4. I see a lack thereof, but a carbocation can always resonate between, so it is continuous. Resin structures can form. On top of that, even though we have an sp3 hybridized oxygen, which is going to not be planar, remember sp3 is going to be tetrahedral. If it can contribute to aromaticity, it'll force itself to be planar. This is something you guys should remember from test 1. So if I have 4 pi electrons, that's not a Huckel number. 6 is a Huckel number. So if I were to contribute these two, right, it would be 2, 4, 6, that would be a Huckel number. And this would be continuous because it would just form resonance structures here and then resonance structure there, all that stuff flip-flopping around. That's going to meet our criteria for aromatic. There we go. Now let's look at the next one. Cyclic, yes. Planar, we'll see. Because right now we'd have a sp3 hybridized carbon. It's a very big red flag. Now let's look at our Huckel numbers. 2, 4, 6, 8, 10. Those are Huckel numbers. However, we have to visit back to our sp3. Right now, this has a hydrogen. It doesn't have a lone pair. It won't force itself to be planar. And the fact that that's sp3 can't force itself to be planar and thus breaks the continual flow of electrons right there. There's a break right there. That's not going to be aromatic. It's not going to be aromatic. Now let's look at the next one. Cyclic, yes. Planar, hopefully. Let's look at the Huckel numbers. 2, 4, 6. Perfect. However, we have this one. All right, if I had 2, 4, 6, I'm missing this carbon. Now here's a situation where it's in a catch-22. Because even though this could hypothetically contribute to resonance structures, right? This could form here, and then this would form to a lone pair there. It would be continuous, but if this were to contribute, it would be 8 total pi electrons. 8 is not a Huckel number. So if I were to look at these 2, 4, 6, even though it's a Huckel number, it's not going to be continuous. Because if it included this and made a full circle, it would be anti-aromatic. But if it weren't, it wouldn't be continuous. And it's in a lose-lose situation either way. So it's going to be a catch-22, not going to work. Now let's look at this ion. Is it cyclic? Yes. Planar? Yes. Huckel number? Hopefully, let's take a look. 2, 4, 6. 2, 4, 6. Those pi electrons are circulating throughout every outer atom. If this were to contribute, even though this is going to be sp3, it's going to force itself to be planar. And this would be cyclic, or continuously cyclic. This is going to be aromatic. So 2 out of the 4 are going to be aromatic. All right, now here comes some of my favorite questions. Acidity, all right? Acidity, it kind of comes naturally once you get into it, right? If you have an activating group, an electron donating group, it's going to be less acidic, like we have with enols. But if you have an electron withdrawing group, that's going to be more acidic because you're pulling electron density away from the proton. Excuse me. So for this one, I say that we have a commonality: phenol, 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 phenol. Now let's take a look at the electron density. So I know that aniline and CH3 are going to be putting electron density into the system. It's going to be electron donating. And they're going to be, here, this one's going to be neutral. They're going to be stabilizing the anion. However, for chlorine and bromine, these are going to be electron withdrawing. So they're going to be pulling electron density away from the proton. So I can deduct that these are going to have our most acidic protons. Now, which one's going to be the strongest acid? Whichever one's going to be the most deactivating. And the answer would be bromine. If you look at the chart, bromine's lower on the list. It can align with those p orbitals in the least amount because it's so freaking big. If you look at the carbon p orbital, they do not line up at all. Bromine's way too big. It's going to destabilize any kind of charge you have, and it's going to be really bad and a very big deactivating group. Probably not as much as other deactivating groups because it is still mild. All your halogens are mild. But compared to chlorine, it's still going to be very acidic. So if I know that this is going to be the most acidic, circle the one with the strongest acid. Now let's look at the one that's going to be the weakest acid. So the weakest acid means that there's the most amount of electron density being stabilized. It's donating electrons and stabilizing that proton or that negative charge. It's going to be this one, right? if OCH3 is going to be pretty much very, very high on the list, it's going to be a strong activating group. It's going to stabilize and donate electrons to the system. It's going to destabilize the anion that would be formed, right? Because you're putting pouring electron density into a negative charge that's going to be very unstable. Because remember, if you pull off a proton, that's going to be a negative charge. So if you already have electron donating regions into that negative charge, it's not going to look good. All right. Circle the compound that reacts fastest with electrophilic aromatic substitution and put a box around the one that reacts the slowest. So in terms of reacting the fastest, now we look at the opposite, right? If it's reacting the fastest with electrophilic aromatic substitution, we're looking for the highest activating group. And this table, I hate to say it, you should know, but it does follow a common trend. If you're confused about the trend, look at my videos. I summarize all of it. It's pretty great. So out of these is the same ones, right? Aniline, benzene, a methyl group, so toluene, chlorobenzene, and bromobenzene. So the most activating group, even though it's going to be the weakest acid, it's going to be the most reactive to electrophilic aromatic substitution. It's going to be very electrophilic. On the flip side, it's going to react the slowest. Why is that? Because it's the most destabilizing. It's going to slow down that rate of reaction very, very much because it's bromine. It's going to withdraw more electrons away. It's going to donate electrons toward that ring. Okay. Directing effects. Circle all hydrogens that are likely to be substituted by electrophilic aromatic substitution in the reaction. For this, we follow whichever one's higher on the list. All right? Whichever one's higher on the list. So, if I'm looking at nitro and chloro, which one's higher on the list? It's going to be chloro. So I know that these protons are going to be pulled off. Because chloro is para-ortho directing. Circle the one hydrogen that is most likely to be substituted by electrophilic aromatic substitution in the reaction. That's going to be 1, 2, and 3. So for our toluene, phenol, and our chlorobenzene, which one's going to be the most directing? The answer will be phenol, right here. The OH is going to be the directing group. So it can add either here or here. Now here's the question. Circle the one hydrogen that is most likely to be substituted. This one is sterically hindered, while this one isn't. So if I had to pick between the two, it would be this one. All right, this one would be least sterically hindered. Okay. Now, we're looking at the resonance structures. Draw all resonance structures for the structure below. Compare all structures, circle the resonance form that contributes to the most to the hybrid. If two or more contribute to most of the hybrid equally, circle all that do. One of my favorite questions is resonance, right? If you guys think back to your semester 1, resonance might not have been the best thing, but right now, resonance is like the back of your hand, right? It's like breathing for you guys. So I'm looking at this. I know I'm making a personal note. There's going to be sp3 hybridized. This does not play a role in resonance. Not going to play a role in resonance. So the best thing I'm going to do is just door hinge maneuver over here, door hinge that, and thus I would get something like this. Like this. If you guys remember, the definition of an ortho-para directing group is that whatever branch you have has a lone pair and create an extra resonance structure to stabilize whatever positive charge you make. So another resonance structure I could make would be moving these down and having this. Perfect. Now there's another resonance structure, and you might be thinking, well, I can always just move this back here, positive charge here, right? But remember, all these resonance structures are pretty much equal to each other. So I would just make note, instead of doing the 2 steps in one up here and then up here, I can just imagine this going over here, right? If I were to do a resonance structure like this, which is still valid, and you can draw it however way you want on your mechanism page, it's going to look like this. gonna look like this. I don't know if you guys see this, but if you look at this, maybe this guy gives you guys nightmares, right? Look, it's an enol. Ooh, ooh. Not actually. It's part of that benzene ring, but still. Ooh, scary, right? Are you guys scared? Good. Okay. Now let's look at the electrophilic aromatic substitution mechanism. So I'm looking at this. I have Br2. You might be thinking, well, where's the FeBr3 or that Lewis acid catalyst? The thing is, we don't need it. Because if we have a strong activating group, like this amine right here, there's an amine group, a substituted amine, it has that lone pair, it loves that positive charge. It's going to stabilize that positive charge, and it doesn't really need that catalyst. The catalyst is built in pretty much. So what would we have? We would have a double bond breaking. Excuse me. I think it wants us to do the pair position. So I'm going to break this double bond. Oops. Yeah, this double bond. And it's going to form something like this. I'm just going to do this for that. You guys know what I'm talking about. It's going to form positive charge here. And that H is still retained. And now the new Br is going to be here in the pair position. And the pair position. And we create a carbocation. So that first step is going to be the rate determining step. The formation of the carbocation is the rate determining step. Now we have different resonance structures. We saw those resonance structures up above in the very top of the page. Door hinge maneuver looks something like this. Door hinge maneuver again looks something like this. And because we have an ortho pair directing group, we know that that lone pair does something else. It can create another resonance structure. Something like this. Again, same deal, same thing we saw up there. Same deal. These are all going to be resonance structures. The real image, the real way that they exist is going to be in a hybrid equal to all each other. All right. Now let's take a look at the mechanism. All right. Well, if we have this electrophilic attachment, if we look at a base, let's say the base, some convenient base were to come here, come and take that hydrogen, well, then that lone pair would reform and recreate that double bond, creating something like this. And the bromine right here. We still have the bromine from the solution, or the bromide specifically. And we still have that protonated base, whatever convenient base we have. It could be water, or it could be the bromide. Whichever one works, that's fine. Honestly, you can just keep it as BH. What we're looking for is going to be this and this. This you can write just to clear all your bases. Huh, cool base pun. But these main two are the main things we're looking at. Your final product and whatever side products we have. This is kind of assumed, but you're welcome to write it just in case. Oh boy, let's look at some synthesis. Let's take a look. Well, right here, I can tell I have a methyl group. Methyl group is stakes, and I'm trying to add a chloro group that's going to be meta. And that might pose an issue for you guys because you might be thinking, well, hey, if I were to just chlorinate it, I know that methyl groups are going to be ortho-pair directing. That's no bueno. Ortho-pair directing. So how do we do it? Well, it's pretty easy. What if we were to think, okay, one of the most broken pieces we can have in a benzene synthesis is going to be our NH2s, right? If we were to nitrate it and then we were to reduce it into an NH2, right? We can turn that NH2 into literally into a diazonium salt, and then that diazonium salt can turn into literally anything. Well, if that happens, we can, well, I pretty much just said it, we can turn it into anything. The thing is, if we were to add the nitro group, the nitro group's going to add still orthopara. How the heck are we going to add the chlorine? Well, if we were to retrosynthesis may not be the best thing here, but I would honestly just start writing out ideas. So the first step would be NO3, H2SO4. And this is the first step because if I were to try to figure out how to, deal with this via diazonium salt, first I have to do is nitrate it, right? Let's see what we can do. If I have a nitro group, I can try to see if I can push meta, but then the methyl group would take priority still. So I were to turn it into an NH2, well, let's see what we can do from there, right? There's a lot of different steps and checkpoints you can have at each simple step. But right now, the fact that it's meta is kind of throwing us in for a loop. So if I were to nitrate it, it gives us at least a first step. If I were to do a nitro group, nitrate it, I would get CH3, the ortho position, and you would get the para position, right? Now, for here, if I were to add, let's say, a Cl chlorinated, it would add either right here, which is not what we want, or right here and right here, which is not what we want. So I know that we kind of want to turn it into an NH2 group and see what we can do from there. Okay. So if I were to do that, let's do this one. Actually, we can do either one, but if I were to do this one, for example, H2PD on C. Oops. NH2, we have an aniline. And for an aniline, we can chlorinate it, and now this is taking higher priority than the CH3. So the things that are ortho to the aniline are actually going to be meta to the methyl group. So if I were to chlorinate it, Cl2, I'll get something like this. You might be thinking, well, Patrick, why don't you have a Lewis acid catalyst? The answer is, if you remember, aniline is going to be a strong activator. Strong activators, they have that catalyst built in. They're that reactive. So the NH2 doesn't really need the FeBr or FeCl3. We'll add here. And now we can just turn into a diazonium salt and get rid of it, right? So if I were to do one, oh no, and then we would to react with like NaNO2, HCl, 0 degrees Celsius, all that solvent stuff. Turn into the diazonium salt. It looks something like this. You guys know that. Diazonium salt. 2 would be, I think to remove it, it would be phosphorus acid. Phosphorus acid? Phosphoric 3PO2. Just to remove it. Just to remove this. And here's the cool thing. If I were to go from here, just to cover my bases, well, if I were to turn this into aniline, it would look like this. NH2, CH3. If I were to chlorinate it, it would add here or here. H2, Cl. No matter what we have, let's take a look. Whatever methyl group we have, chloro is meta. Whatever CH3 we have, chloro is meta. And we can still treat it with the same stuff. So this is one of the cases where we could go with either one. All right. This is just the general thought process I have. Synthesis is a little tricky because it's honestly trial and error, right? And I know as a STEM major, you guys might not be the biggest fans of a trial and error, but honestly, this is synthesis. You can try to do retrosynthesis, see how you can get there, and then just try stuff out. So if I were taking final, personally, I feel very confident in synthesis, so I would go ahead and do it. But if you're not confident with synthesis, I would honestly save it for the last. Because if you're not very good or you're not very confident in synthesis, it might take a while because it is trial and error compared to the others. Save it for last. Don't be afraid to do that, right? Oh boy. Now let's take a look at the reactions. We have an amide right here, right? We have an amide. This would be an N-phenyl ethanamide. Ooh, some nomenclature, right? So if I were to react it with Br2 FeBr3, well, an amide, nitrogen amide, that's going to be a moderate activator. Excuse me. It's not strong enough to add by itself, so we need that bromine to have the FeBr3. Excuse me. So if this is going to be a moderate activator, I know that's going to be ortho-para directing, ortho-para. So my two products would be something like this. Whoops, let me make it a little bit prettier. Something like this. CH3. Here, watch this. Let's cheat the system a little bit. Something like this. It would be para and ortho. Now, if I were to read the directions, it would say, give one product for each of the following reactions. Well, if I had to pick between the two, I would pick this one because of steric hindrance. Pick the one with the least amount of steric hindrance. That should be pretty clear cut. You guys are already at the end of semester 2. You guys should know why steric hindrance is better. Actually, yeah, I'm probably going to explain further into that. Yeah. All right, perfect. Now we have to look at our Friedel-Crafts acylation, right? Now be careful. If you remember your Friedel-Crafts alkylation, alkylation is prone to carbocation rearrangement. But for acylation, that's not the case. And if, for acylation, we just add to wherever we're going to. If I have a xylene, a metaxylene right here, I know that it's going to be ortho-para directing. So for the first CH3, the spots that it wants to add is going to be here, here, and here. If I'm looking at the second carbon up above, it's going to want to add to the same spots. Whoop-de-doo. Now, if I'm looking at these three spots, I know this one's probably going to be a no-go, right? Steric hindrance, again. So I'm looking at mainly these two. So if I were to add to either one, I would get something like this. CH3, CH3. Whoops. Where the acylation would add either here or here. Now, if I had to pick between the two, steric hindrance doesn't have any kind of role to play because these are going to be symmetrical. They're going to be symmetrical. And if you're wondering why that is, take a look back at your semester 1 notes, right? If I have a plane of symmetry right here, right, directly symmetrical, CH3, CH3 are equal. This spot is no different than that spot. No different than that spot. I could just pancake flip among that same plane of symmetry. So all I need to put is the 1. Now we have another acylation right here. If I were to add, I would take a look at our groups. I know fluorine and chlorine are on here. Fluorine is going to want to add here. Chlorine is going to want to add here. Now, which one takes priority? Whichever one's going to be higher on that priority chart. And the answer is going to be fluorine. Fluorine is going to be least deactivating, relatively the most activating. So we're going to follow those rules. So if I'm going to add here or here, I can add to either one because, again, there's a plane of symmetry right here. No matter which one I add to, it's going to be the same. And it looks something like this. Now, here's a real doozy. We nitrate it and then we reduce it. And this is going to be a tert-butyl group. I know that alkyl chains, no matter what alkyl chain we have, is going to add ortho-para. The thing is, a tert-butyl group is going to be so sterically hindered, it's going to add ortho like 1% of the time. It's not going to happen. Pretty much everything's going to add para, all right? Even though ortho-para does happen, para is going to be the major product without question. So I know for step 1, I'm going to get a tert-butyl group. and add an NO2 group. If I were to reduce it, I would turn that NO2 into an NH2. Perfect. Now let's take a look at OH. Phenol, fuming H2SO4, Br, FeBr3, and H2O. If I were to do the first step, it would do this. If I were to do fuming H2SO4 on a phenol, it's always going to add para. Why is that? You don't really need to know why, you just need to know it. If I were to brominate it, well, which one takes priority? If I have a strong activator like phenol, that's going to be way higher on the list than sulfuric acid, or the sulfate group. So it's going to add ortho to our OH groups. So I would do step 2, it would do something like this. OH, SO3H, and Br. Now for the final step, H2SO4, or excuse me, H2O and heat, we just remove the SO3H, and we would just get a bromophenol, like this. Final answer. H2O and delta just removes that SO3H group we have. So SO3H group can be thought of as a protecting group. It just protects and blocks that pair position from being activated. Is it an extra step? Yeah. It's personal preference, whichever one you have. If you see it on a reactions page, you should know what it does. But if you see it, or if you want to use it in a mechanism, you don't have to. You don't have to. You can still filter stuff out. We would like you to minimize whatever you filter out, but honestly, if it works, it works. Now we have a trimethyl benzene. Trimethyl benzene. Try to look. There are a couple places to add. They can add here, here, or here. All 3 places. Because if I were to add here, it would be ortho to this and pair to this. Checks out. If I were to add here, it would be ortho to this and ortho to this. If I were to add here, actually, it would not add there. It's going to be, actually, no, I can't. It's going to be ortho to this. So let's actually color code it. So I'm looking here. This one wants to add here. If I'm looking at this carbon, wants to add here and here. If I look at this carbon, it would want to add here and here. Now, here comes a real cool process of a deduction. Let me erase this noise over here. Now it becomes a process of deduction. If I know that these two are going to take priority over here because there are 2 CH3s, 2 out of the 3 are voting for these spots, that's going to work. All right, this one's not going to happen as likely. On top of that, between these two with the most votes, this one's going to be sterically hindered. So this is going to be the best choice. This one's ruled out because it only has 1 vote, and this one's ruled out because of steric hindrance. So the major product, if you're to nitrate it, would go into here. CH3, 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 and then NO2. Perfect. All right. Now let's take a look at a dibenzene ring, right? If I were to look at these, I would go ahead and identify, okay, one of them is going to be activated, one's going to be deactivated. The O terminus is going to be moderately activated. The C terminus is going to be moderately deactivated. So if this entire, if this entire thing were to react, I know that the moderate activator ring will react because out of the 2, which one's going to want to react with CO2? It's going to be the moderate activator. So if that's the case, I know that this ring is going to react. And if I know that that ring is going to attack, that ring is going to react, is going to add ortho and para. So let's recap. Out of the 2 rings, this one's going to be the most reactive. On top of that, it's going to add ortho para right here. So I have 3 different spots. So if I were to chlorinate it, it would actually add to the pair position. Why is that? Well, again, we have to have 1 product. If I had to pick between ortho and pair, there's ambiguity. I would pick the one with the least steric hindrance. Thus, pair position would make the most sense. And if you're confused on that, I think there are problem set questions you can refer to look at it, or to look at. Yeah. Oops. There we go. Perfection. All right. Now here comes a real killer. Aniline. So your aniline rules, if you have a deactivating group, right, it will add alpha in the other ring. If you have an activating group, it's going to add alpha to the same ring. So let's recap what I just said. Remember, when you add things to aniline, it can only add to your alphas, right? These are our alphas, alpha, 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 alpha. And these are going to be our betas, beta, 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 beta. Have you guys ever seen that video, like that one cringe kid, like talking to the teacher, like, I am the alpha. The alpha doesn't listen to the professor. And the professor doesn't care. I love that video. That's so funny. So funny. Okay, back on track. We have alpha carbons, and they're going to add there. Now, the rule is if you have a strongly deactivating group, it's going to add to the alphas on the other ring. But if it's a strong activator, like an ether, remember the ether has that oxygen lone pair that can donate those electrons, it's going to add to the alphas in the same ring. Furthermore, it's going to add to the closest alpha carbon. If you're still confused about this, there is a video. Just review the videos from test 1. So if I'm going to add to the alphas, CH3, it's going to add here, NO2. Now the minor product will also add here, but again, we're looking for the major product. Just how the minor product can also add there, maybe like 20% of your yield will add there. Small percent of your yield might add there. We're looking for the major product. Looking for the major product. All right. Now let's take a look here. What the heck is that? We have a sodium methoxide and heat. How the heck do we do that? Well, we should know that if we react any kind of benzene ring or substitute benzene ring with a base, especially a strong base, a nucleophilic base, we're going to be doing a nucleophilic aromatic substitution. Not electrophilic, but nucleophilic. Excuse me. So instead of the SEAR, we're going to be doing the SNAR. The SNAR reaction. It's basically kind of like the electrophilic aromatic substitution, but it's a nucleophilic aromatic substitution where we substitute whatever leaving group we have, like a halogen, with whatever nucleophile or strong base we have. And remember, that ring has to be strongly deactivated. So let's go ahead and take a look at our checkpoints. Good leaving group, check. Strong deactivator, check. It can go through the SNAR reaction. Those are 2 requirements. So if you react it with a strong nucleophile, like that strong base, we're going to retain that NO2, but the Cl would essentially just be kicked off and be replaced by whatever nucleophile we have. This would be the answer to step 1. For step 2, we reduce it. So what can we reduce? We can reduce the NO2 into NH2. There we go. And this would be our final answer. There we go. All right, final one. So if we have toluene, if we were to nitrate it, well, where can it add? It can add either here or it can add here. All right? If you were to add to either one, nitrate it, CH3, NO2, or CH3, NO2, or to do step 2, reduce it, NH2, CH3, NH2. Or to do this one, this would be the, what is it? I think that's the HONO. KI. We would replace whatever diazonium salt we have. We replace that with iodine. Oh, if I had to pick between the two, the answer key says this, but I'm a little puzzled why. Looking back at it. Hmm. Anyone in the chat know anything? What is that? I'll trust my gut. Put it here. I'll probably pick this one. Iodine. There aren't any rules against nitrating or rules about an ortho position being less yield. You're right, the answer key does say the top one. Hmm. I'll go with the bottom one. I will go with the bottom one. Either one. Yeah, either one would work. The heat, nah, the heat doesn't do anything for that. I'll probably post something in the group chat later on. Does Tyler prefer ortho? No, it shouldn't. Unless the textbook says so. Maybe I missed something in the textbook.
I looked it up and it's saying something about like the electric effect, like
Really?
electroinductive effect. Yes, I don't know what the hell that means, but
Electroinductive effect. So this one would be preferred because of the electroinductive effect. Let me see. Well, now you know. One of those weird textbook thingies. Great. Well, what a note to leave off on, right? I think this would be a perfect position to take a little break. I'm gonna stop the recording right now. It's on file and on the recording. Shoulda, coulda, woulda. On the drink. All right. If I were to rank the beers, right? Me and my friends have talked really deeply about this. There's good beer and then there's shit beer. Out of the good beers, my top three are going to be, excuse me, Heineken, Stella, and Corona. Corona. And then for the shit beers, it would probably be Busch Light at the top. I love a good old Busch Light. I'm from Southwest Virginia. We love them Busch Lights, man. Medical school admissions watching this. Oh my God. Yeah. What about Guinness? What about Guinness? It's a post end of the night kind of deal. I'm not something you want to sip on. Like imagine like drinking Guinness and like chicken wings. That's not a good combo. Not a good combo. Digital footprint, bro. I already like recorded a video of me like chugging wine last semester. My digital footprint's already like tarnished. Miller High Life snubbed. Bro, Miller shit. See, the only good beer is a free beer. On God. On God. I'm gonna blow my nose one more time, then we'll get to test two. Fuck. Fuck. Ah. All right. We're here. We're here. Patrick's actually pulling Jeeves every time we go to the bathroom. Yeah. Yeah, okay. No one else. Marina knows. Yeah. All right, test two is going to be extremely, extremely weird because it's a hard left turn from pretty much everything you've learned. All right. And when you're looking at test two, well, there's a bunch of combined spec. There's a bunch of equivalent carbons, equivalent hydrogens. You're looking at you're looking at a lot of general knowledge, and then you're looking at combustion reactions. Now, for these specific test two material, the highest yield is going to be straight up your combined spec. Because for your combined spec, you're pretty much integrating everything from IR, proton NMR, and carbon NMR. I think these are going to be extremely high yield for your MCAT. I mentioned this before, but even on my MCAT, I had proton NMR questions. I didn't have an IR question, but I had a proton NMR question. And then I also had further questions, just like equivalency, uh, and what the peaks would look like. Yeah, I think those were the questions. Anyway, where to look at this? All right, compound A gives 91.61% carbon and 8.39% hydrogen by elemental analysis. If I were to add this up, let's do 91.61 plus 8.39. That'd give me a straight 100%. 100%. That tells me that there is no other element in this. So if there's no other element in this, the best thing to assume there's a hydrocarbon. And when there's a hydrocarbon, there is the rule of 13s. So if I have a molecular ion peak of 114, I know that that's our molar mass. So in order to take our molar mass, divided it by 13, that would be 11.076. Now, I don't even need the fact that it's a hydrocarbon to do the rule of 13s, because remember, the rule of 13s is straight up just a place to start. If you were to have, let's say, a molecular mass of 136, no elemental analysis involved, you can do rule of 13s to figure out a hydrocarbon chain. And from that chain, that just gives you the simplest hydrocarbon chain possible. You can figure out the degree of unsaturation, and if it's invalid, you can move on. Let's subtract the carbon and then subtract 4 hydrogens to make an oxygen, right? Again, the rule of 13s is just a place to start, assuming that it's a hydrocarbon chain. Most things that we give you are not straight up hydrocarbons, and furthermore, they usually have oxygen or nitrogen. But usually what we give you don't follow the rule of 13s. And again, it's just a really nice place to start where you can actually get a sensible molecular formula and then just try to trying to think of the right word. Once you have your hydrocarbon, extrapolate that and see if you can make an oxygen or nitrogen from it. But thankfully, for this situation, we just have a straight up carbon and hydrogen. There is no oxygen involved. Perfect. Very perfect. So we would just take a look at our simplest carbon chain. So our whole number, that's going to be our C11, right? And 0.76, well, if we were to multiply that by 13, 0.76 times 13 times 13, that'd be pretty much 1. This is 1, H1 plus whatever whole number we had, which was 11. Our simplest chain would be C11H12. Let me make sure that that degree of unsaturation is going to be sensible. 11 minus 12 divided by 2 plus 1, that's going to give me 6. That's going to be C11H12. Why is that? Our degree of unsaturation is valid. Our molecular ion peak adds up to our molecular mass. Everything adds up. This is the simplest hydrocarbon formula we have, right? Degree of unsaturation of 6. We probably have an aromatic ring and then maybe 2 pi bonds elsewhere. And this is going to be compound A. I'm just going to make a special note of that. Compound A. If compound A were to react with H2 and Lindlar's catalyst to give compound B would give a molecular ion peak of 90.35 carbon and 9.65 hydrogen by elemental analysis, and gives me a molecular ion peak of 146. what is the molecular formula of B? Well, first off, let's look at the molecular ion peak, 146 and 144, right here. What's the difference? 2. There is a difference of 2 molar mass units. What is the molar mass of 2? 2 hydrogens. The best bet is if we were to hydrogenate stuff. We were to just add. Man, I sound crazy already. Yeah, I know. We were to add 2 hydrogens to whatever molecular mass we had. So I would say, hypothetically, that my best bet is going to be C11H14. But let's double check, right? Let's double check. Let's take a look at the logic. If we had 144, we had C11H12, H2 Lindlar's catalyst. If we were to add 2 molar mass units, which happens in Lindlar's catalyst, we remove a pi bond and we add 2 hydrogens, we would get C11H14. That'd be 146. And what does Lindlar's catalyst act on? Alkynes. All right, Lindlar's catalyst acts on alkynes just to make it into an alkene. It doesn't fully reduce it into an alkane, but just retains it to an alkene. So it'd be alkyne to an alkene. And if we were to do the rule of 13, it's 146, excuse me, divided by 13, that would be, let's do the math. 146 divided by 13, that would be 11.2307. So I know out of C11H, let's do minus 11, so 0.23, times 13, that'd be 3, plus, or H3, plus our original 11, that would be C11H14. Checks out. C11H14. Boom. And this was one of the test errors that we did clear up during the test. Compound A, same compound A from up here, were to react with H2O, H2SO4, and HgSO4 to give compound C. Compound C gives an even more disproportionate amount of carbon hydrogen, 81.44, and 8.70 of H. By elemental analysis, it gives a molecular ion peak of 162. Hot damn, 162. What is the molecular formula of compound C? Well, okay, if I know from my knowledge on Lindlar's catalyst that Lindlar's catalyst can only act on alkynes and it creates an alkene, everything checks out. I know for a fact that this is going to be an alkyne. It's going to be an alkene. If I have an alkyne reacting with H2O, H2SO4, HgSO4, what does that make? That makes a ketone, right? That makes a ketone. If I were to react a triple bond with this, I would create an enolate, and then it would tautomerize into a moderately keto form, and we would add an oxygen to the entire thing. Well, that makes things a little bit more different. So let's take a look. We have C11H12, remember, compound A, becoming some unknown compound, but through the reaction of H2O, H2SO4, HgSO4. If I start out with compound A being 144, becoming 162, that's a difference of 18 molecular mass units. So that means I'm adding an oxygen and adding 2 hydrogens. It's not likely that we're adding 1 carbon and 6 hydrogens. That doesn't really make any sense. What kind of reaction do we have that adds that? What we usually see is going to be an oxygen and 2 hydrogens. We're adding H2O across everything. Pretty much. Okay. So if I'm looking at this, well, if I have this, I'm adding 2 hydrogens and I'm adding an oxygen, well, it would be C11H14O. And that should make sense with here. If I have C11H14, the difference between 146 and 162 should be 16. So if I were to take 162 minus 146, 16, I'm only adding an oxygen. So that makes sense. I'm adding a I'm adding two hydrogens here. I'm hydrogenating it. I'm reducing that alkyne into an alkene. And here I'm reducing that alkyne into a ketone. So my most likely molecular form is going to be C11H14O. Now, here's the real caveat. Patrick, I don't like the way you did it. Well, if you don't like the way you did it, there's another way. You could use your elemental analysis and you can find the molecular the molar mass concentrations or ratios between each, standardize them, divide every single standardized item by the lowest mole number, and figure out the molecular formula from there. If you don't know what I'm talking about, take a look at your notes. It's in your notes. That's the way Dr. Berg did it. That's the way you did it for your problem set. But for me, I did this via logic. You can honestly do this entire page the way I did it and verify it with Dr. Berg's version, vice versa. Whichever way you want to do it, that works out. But for me, the logic plays out a lot better. Now, granted, for me in my position, I know, seriously, I know what these reactions do. H2O, H2SO4, HgSO4, and what Lindlar's catalyst does. That's one of the big advantages of knowing what your your semester one reactions are. You have this kind of advantage. So honestly, whatever works for you, you can retrospectively look back on your semester one reactions, or you can just try to, math your way through this. But this is the way I did it with minimal math. Now for our degree of unsaturation and for our functional groups, we already did that. So compound A in the very beginning, we already calculated our degree of unsaturation of 6. But for B, if we got rid of a triple bond, making it into a double bond, we remove a pi bond. So that degree of unsaturation should be 5. And that checks out. If we have C11, so 11 minus 14 over 2, so 7 plus 1, 11 minus 7 is going to be 4, plus 1 is going to be 5. Checks out. Degree of unsaturation for C is also going to be 5. Because same deal. C11 minus H14 over 2 plus 1 equals 5. Excuse me. Oxygen does not play a role in degree of unsaturation. Where's the functional group for A? Alkyne. B, alkene. C, ketone. Here, let me give you guys a minute to absorb this. Man, coming in hot. We did the entire page in what? 15 minutes? That's a good sign. One, two, three, 4, 5, 6. Wow. 7. Oh my God. This is really good. This is really good. If we don't remember the last reaction, what's a good way to deduce a functional group? Excuse me. Yeah. Which one is that you're drinking? This is going to be Corona Premier. Corona Extra and Corona Premier are really good. All right. Let's do a quick little mini break. Who in the chat is 21? Follow-up question. Who in the chat going to TOTS on Friday? I'm gonna be there. Pull up. Pull up. Pull up. Pull up the TOTS. And this is still recording. All right. Hypothetically, pull up the dots. Hypothetically, pull up the dots. Okay, let's keep going. Let's trudge along. For each of the following structures, indicate how many equivalent carbons are present. For equivalent carbons, perfect. Well, let's just go ahead and get started. For equivalent carbons, well, there is no plane of symmetry for our bromochlorobenzene. So we have 1, 2, 3, 4, 5, 6. 6 unique carbons. 6 unique carbons. Why is that? Well, each of these carbons are going to be very unique. This one's one geminal to the bromine. This one's geminal to the chlorine. This one is 1 carbon away from bromine. This one's going to be 1 carbon away from chlorine and 2 carbons away from bromine. And then these are going to be different. Now, for this one, we're going to have 1, 2, and this is going to be 2. Why is that? There's a plane of symmetry right here. This carbon is going to be identical to this carbon. This carbon is going to be identical to this carbon. For this one, we're going to have 4, because we're going to have this unique carbon, this unique carbon, this unique carbon, and this unique carbon. But the weird thing is this unique carbon is going to be the same as this carbon. They're going to be identical to each other. So I'm just going to have the 1, 2, 3, and 4. Because this is going to be the same as this. And for this one, I'm going to have, well, let's take a look. If I have plane of symmetry right here, this carbon's identical to this. This carbon's identical to this. And this carbon's identical to this. It's going to be 3. And then for this one, we have another plane of symmetry. This carbon is going to be identical to this. This one is identical to this. And this one's going to be symmetrical by itself. This is also going to be 3. All right, now let's take a look at whether things will show up as multiplets, quartets, triplets, doublets, or singlets. For HA, if I were to look at HA, what would it show up as? Well, if it's next to only 1 hydrogen, it's going to be a doublet. HB, on the other hand, is going to be connected to 3, 6. It would be a multiplet, specifically a multiplet 7. You don't have to specify unless told otherwise, but it would just be a multiplet. HD is connected to no hydrogen, so it's going to be a singlet. HE is going to be connected to 2 hydrogens, right? Even though this can be drawn up as CH, you can ignore this. CH is connected to the 2 hydrogens, so it's going to be a triplet. Then HF is going to be connected to 0, 1. It's going to be a doublet. If it's only connected to the 1, well, 1 plus 1 is going to be 2. It's going to be a doublet. Now let's take a look at our data just raw, right? So if we look at our data, our IR data for this first one is going to be 831. For 831, that's very indicative of just pairs substituted, right? You can look this up on your correlation chart, which is going to be given to you. But if it's given to you 831, it's going to be in that 850, 800 range. There's only that one peak is going to be para. Para substituted is going to be C. Oops. Oh, shit, I lost my page. There it is. Okay. Now for the Proton NMR, if I have 2 doublets, I have 2 possibilities, either A or C. And the thing is, for A and C, our 2 groups are going to be identical, right? So if I were to look at HA, it's actually going to be identical to these. HA. It's going to be identical. So it's only going to show up as a 4H singlet. So if I have 2 doublets, it's most likely going to be these. HA HB. So this is going to be A. Now for the third one, protein NMR data, we have three different types. So if I already deducted that the first, or not the first, the C structure is going to have only one type of carbon and hydrogen, only one type of hydrogen, and A is going to be two types of hydrogen. If I'm looking at three different types, it's going to be B, and that checks out. If I have HA, HB, HB, and then HC, that's going to be compound B. Now for the carbon NMR, if I have three different types, let's take a look. If for the first one I have, let's erase this. If I have A, geminal to the bromine, B, C, three types. My best bet is going to be A, but let's double check. A, B, C, D. These are going to be identical to C and B. There's going to have four different types. Four different types. And then for this one, I'm going to have A, B, 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 A. These are going to be what's identical, where your Bs, your dark blues are going to be one carbon away from the bromine. So A is our best bet. Now, if we were to have two types, well, that best suits going number C, or letter C, because what we explained, right? We have our geminal bromines, which is going to be one type of carbon, and then our middle ones, which is all going to be equally one carbon away from the bromine, right? And let's take a look at the IR spec. For the IR spec, the first thing we look at is going to be our OH and NH2 region. And here we have our peak picker of 3382 and 3292. The fact that there are two peaks means that we can rule out OH and COOH, carboxylic acids, and hydroxy groups. Excuse me. If that's the case, we have two different peaks, and this should make sense. If we have two different peaks, then that means we have two different NH bonds, two different polar NH bonds, and that should check out. This means that it's going to be an amine group. Amine group, why? Well, we ruled out COOH because it's not a broad, ugly peak, and we've ruled out OH because there is no narrow but still kind of broad and smooth peak right there. If I have two distinct peaks, the peak, pick, is going to be an NH2 because I have two different NH bonds. This is aromatic. Well, let's take a look. I have no sp2 bonds. I have no overtones. I have no I do have 1600 and 1450, but I have no outer plane bending. The fact that I don't have any of these means this is going to be no. I don't have all the requirements. If I look over here, let's take a look. I do not have any OH peaks, but I do have a carbonyl peak. So if I have a carbonyl peak, I know that there is at least one path I can go around. I have ketones, aldehydes, esters, and carboxylic acids. I can rule out carboxylic acids because I don't have an OH, but I still have the others. So let's double check and make sure we don't have Fermi doublet. I don't see a 2720 or a 2820. No aldehyde. So it's either going to be a ketone or an ester. Now for an ester, I know that I'm expecting a carbon-oxygen bond. And this is going to be this peak right here. Anything between that 1000 or 1200 peak is going to be that ester bond. My best bet is going to be an ester. Is it going to be aromatic? Let's double check. I do have some overtones, but I don't really have any sp2. No sp2. 1450 I kind of have, but I don't really have a 1600. Not looking good for aromaticity. All right, now let's take a look at this one. So let's take a look. I don't have any OH bonds. No OH bonds over here, not carboxylic acid, not alcohol, but I do have a 1700 peak. I have a carbonyl. I know that I don't have a carboxylic acid because a carboxylic acid would have a very ugly peak right over here. So my other options are going to be ketone, aldehyde, or an ester, like we had in the previous one. So let's go ahead and rule out an aldehyde. I do see a 28 something, but I don't really see a 27 something. I don't see those. It's not going to be an aldehyde. Furthermore, I don't really have a major ether peak. I don't have a CO bond. This is going to be a ketone. Now, is this aromatic? Let's take a look. Overtones? No. sp2? No. 1600? No. 1450? Yeah, but it doesn't have an accompanying 1600, so it's going to be a no. It's going to be not aromatic. Now let's take a look at this one. Now look at this ugly mug. First off, I know that there's a carbonyl. Is there an OH peak? Yes, there's a very big, ugly OH peak. My best bet is going to be carboxylic acid. Is it aromatic? Well, let's take a look. Are there overtones? Yes. Are there sp2 carbon peaks? We can't tell. So this one's going to be a neutral dash line because carboxylic acids, they overtake and overshadow our sp2 peaks. Is there a 1600? Yes. 1450? Yes. Is there added plane bending? Yes. It is aromatic. It is aromatic. Now let's take a look over here. Now we finally get into some more proton NMR, right? I've seen lack thereof. First off, what I'm going to look at is, okay, if I'm analyzing the question, the IR spectrum, proton NMR, and carbon NMR, along with the percent composition of the molecular weight is given below. Answer the following questions. Well, okay, if I don't have a molecular weight, but I have everything else, let's take a look. So if I am looking at the carbon NMR, I'm looking at 1, 2, 3, 4, 5, 6. 6 unique carbons. This one's not going to be counted because the instructions tell me so. And then for this one, it tells me, okay, I don't have a carbonyl structure. There is no 1700. There is an alcohol peak right here. If I have an alcohol peak right here, man, how ironic, alcohol. If I have an alcohol peak right here, it's just likely going to be an OH group. Is it aromatic? Well, let's take a look. I do have some overtones. I do have some sp2. I have 1600. I have 1450. And I have added plane bending. It is going to be aromatic. And I've deducted the functional group OH. Now let's take a look at the proton NMR. Now, for CH, not CH, for 6H, this is going to be a Gemino CH3. This is my best bet. But I'm also keeping in the back of my mind that this could be two chemically equivalent CH3s. Just in the back of my mind. A 1H singlet is always going to be indicative of an OH. So we are kind of on the money when we're talking about the alcohol being over here. Excuse me. For our aromatic region being from 5 to 8, 5 to 7, our aromatic region, if I have two H's, that means I have a total of 4 hydrogens. Remember, 2H plus 2H, that's 4H. That means I have a di-substituted aromatic ring, right? I have H, 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 4 total hydrogens. So if I know it's di-substituted, what substitution pattern would it be? If I were to look back here, I have an 827. That is indicative of para substituted. For the para substituted, this makes sense for the 2H and the 2H. If I were to have para substituted here, I know it's not meta because meta has a lot of gunk around it. But if I had para, Well, then I would have two doublets because these would be chemically equivalent and these would be chemically equivalent. So para is a very good choice. And not only that, I have a 1H. So I have a CH bond here. And most likely I have other protons attached because it is a big multiplet. So if I were to put these groups together, let's start with let me make that prettier. Di-substituted benzene ring that I know is going to be para. If I have that CH, my best bet is going to put the two CH3s on it so that they're chemically equivalent and make that CH3 and fill the requirement of that 1HCH being a multiplet. And then what if I were to put OH up here? This would make sense. This would make sense. I have the 1H singlet by itself, an alcohol nonetheless. And I have CH3, a 6H doublet. Because if these are chemically equivalent, they're next to one hydrogen, they should show up as a doublet, which they do. And I have a multiplet right here. So the molecular formula is actually going to come last, which is very ironic. It's going to be C9H12O. And the degree of unsaturation, well, let's count. Let's take a look at the structure. Let's do 9 minus 12 divided by 2, which is going to be 6. That's 6, excuse me. 12 divided by 2 is 6. 9 minus 6 is going to be 3 plus 1. 3 plus 1 equals 4. And this checks out. All 4 degrees of unsaturation are going into our benzene ring. And that checks out. Wow, that's pretty short. All right, well, that pretty much sums up our test 2. So I'm going to stop my share, and I'm going to pause the recording. All right, welcome back to organic chemistry. We are locking in, and we're going to do this final test, which should be pretty good. Right? I hope you guys can lock into. It's only 8:39, and my ass is calling for tots. Oh, how many beers am I in? How many beers am I in? Ah, sweet. A lot less than I expected. Oh, how funny would it be if I just like mid video I projectile vomit? So funny. Okay. Oh, test 3. Test 3. Now when we're looking at nomenclature, this one he kind of like pulled a little bit of a 20 card on you guys. Easier to grade for us, most definitely. But for you guys, this one was a little tough. He's like, man, let me write out the real name. Let's compare the real name to the name given. It's a little evil, and I know that. Excuse me. Excuse me. Right? Well, let's just go and get started. 5-oxo-hexanoic acid. Carboxylic acid takes priority. The carbonyl carbon is on the 5th carbon. This is going to be a yes. 5-oxo-hexanoic acid. 5-methoxypentanoic acid. Well, I know, hey, still, carboxylic acid takes priority. 1, 2, 3, 4, 5, 6. It's going to be hexanoic acid. The fact that I know it's going to be hexanoic acid is going to be no. Next one. 2-hydroxy-cyclohexafluorine 1-one. I know that this is going to be the first one. And I'm going to have to go through the alkene. Alkene will take the priority. It's going to be 2, 3, 4, 5, 6. So I know it would be 6-hydroxychlorohex 3-ene 1-one. It's going to be no. Poop. Let's take a look at the next one. 5-methyl-hex 4-ene 3-one. If I look at this, it would be either 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Out of the alkene and out of the ketone, I know that the ketone would take priority. So it would be the black numbering. It would be 1, 2, 3, 4, 5, 6. It would be 5-methyl hex 4-ene 3-one. It was going to be a hexene, 5-methyl, and then a 3-oxo group. So this would be yes, because that oxo group takes the priority, and it's going to be a suffix. 2-phenyl propanol. Propanol. It's going to be 1, 2, 3. Well, it would be a 2-phenyl, but there's going to be propanol, not propanal. This would be propanal because it's going to be an aldehyde. So this would be an obvious no. Right, now we have 4-hydroxyphenyl, 3-methylbute-2-enoate. Bute-2-enoate. Well, I know whatever I have in the first word is going to be whatever is going to be added to the O terminus. So if I have this one, if I have a phenyl group, well, whatever is going to be attached, kind of like the branch of a branch, is going to be our first carbon. If it's 4-hydroxy, well, that checks out. 1, 2, 3, 4. Now let's take a look at our parent chain. It's going to be 1, 2, 3, 4. It's going to be a butanoate. Furthermore, it's going to be a bute-2-enoate. And on top of that, it's going to have a methyl group on that third carbon. So this would be a yes. 3-hydroxymethylbutanoate. Remember, methyl, hydroxymethyl, whatever that first word is going to be on that O terminus. That O terminus, we only have the methyl group. So the hydroxy group is on the butanoate. It would actually be 3-hydroxybutanoate, not 3-hydroxymethylbutanoate. It would be methyl 3-hydroxybutanoate. So this would be a no. Now let's take a look at this. N-ethyl, N-methyl, 3-hydroxybutanamide. It's like I'm Mike Tyson. N-ethyl, N-methyl, right? I'm super excited to do this organic chemistry. N-ethyl, N-methyl, 3-hydroxybutanamide. Well, let's take a look. I have 1, 2, 3, 4, right? The parent chain coming from the carbonyl going apart from that butanamide or across from the amide, kind of like the esters, right? It's going to be a parent chain. Parent chain is going to start at the carbonyl, 3-hydroxybutanamide. Checks out. 4 carbons. The third carbon bearing an OH group. Now let's take a look at the rest. I have a methyl and an ethyl group on both, or both being on nitrogen. So the locant for both would be N. So this one would not be right. Not be right. N-ethyl, N-methyl, 3-hydroxybutanamide. Oh, that's why. Hydroxy would be here. It would be N-ethyl, 3-hydroxy, methyl, butanamide. So this would be a no. Ooh. All right, dimethyl propandioate. So if I have a malonic ester, right? Stuff we've been dealing with. Well, I know is going to be a 1, 2, 3, a propane dioate, common for all malonic esters. But instead of diethyl, it's going to be dimethyl. It's going to be yes, because I have 2 ethyls on either end, or 2 methyls on either end. And then it's still going to be propane dioate, because I still have the O8, but there's 2 esters. 4-hydroxy pentane nitrile. This is going to be, well, let's take a look. 1, 2, 3, 4, 5. Do not forget to count the nitrile carbon. And not only that, but you also retain the E when you do your alkane nitrile. And the hydroxy group is going to be on the 4th carbon, so it's going to be a yes. It's going to be a yes. Now for the common names. This one's super easy, fun. Is this compound going to be palmitic acid? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Palmitic acid, yes. Palmitic acid is 16. 14 being meristic, 12 being lauric, and 18 being steric. Palmitic acid, I'm pretty sure, is the main biological, at least the main fat used for humans, at least. Palmitic acid. Man, I'm tweaking right now. How many is that? 4? Fuck. All right, let's finish this one. All right. Butyraldehyde. 1, 2, 3, 4. If I know that the common name for butyric acid means a 4-carbon carboxylic acid, butyraldehyde should check out. The answer would be yes. Kind of like propionaldehyde, acetaldehyde, formaldehyde. I think that's the biggest one. The fact that I know that formic acid is a carboxylic acid version. Formaldehyde is the aldehyde version. I should check out for also butyraldehyde. The butyr being the prefix and the aldehyde just being the aldehyde. Dimethyl isophthalate. Well, I know that the isophthalate is going to be the 1,4 position. So that checks out. Dimethyl isophthalate. Actually, no. Wait. Isophthalate. No, 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 no. The pair position is going to be the terephthalate, I believe, right? This would be terephthalate. If they were pair to each other, this would be terephthalate. So this would be no. This would be no. Is the following compound a hemiacetal? Straight up no. This isn't a lactone. This is a lactone, bruh. This is a lactone. It's not a hemiacetal. Oh, shit. No. No. Fuck. All right. Aldehyde 1 undergoes the following sequence of reactions given the following spectroscopic data. What are the structures of 1, 2, and 3? All right. Well, first off, for molecular weight of 72, the fact that it's reacting with a carbonyl tells me that I probably have some kind of epoxide or carbonyl. Because remember, Grignard reactions really like to attack carbon-oxygen bonds, right? Oh. Ooh. So for the spectroscopic data for part 1, if I have a 6H doublet, right? That probably means I have a 6H CH3 CH3. This is the most common thing. Because if I have a triplet, not triplet, if I have CH3 and a CH3, that's going to make the 6H. And if they're both next to a CH, that's going to make that doublet. On top of that, if I have the 1H right here, 1H multiplet, that's probably going to be this carbon right here because next to 3, 6, 6 plus 1, that's going to be 7. It's going to have 7 peaks. And then I'm going to have 9.72, 9, not 9, 1H singlet. What's so special about that? Well, it's going to be between 9 and 10. Your 1H's between 9 and 10 means it's going to be an aldehyde. So if I were to have, let's say, some kind of aldehyde, if I were to combine it with what I had, that's what I would get. I would get the spectroscopic data from uno, dos. This is uno, and this is going to be dos. And tres. This is the simplest compound I can make. And if I were to do the math, I already do the math. It would be what? 1, 2, 3, 4 carbons, 4 times 12, plus 1, 2, 3, 4, 5, 6, 7, 8, 8 carbons plus 16. That'd be 72. Checks out. This would be my compound for structure 1. If I were to react with the Grignard, this is something you can kind of figure out just on your own. 1 serving, it would attack here. It would form HCO, CH3, CH3, C6H5. That's going to be a phenyl group. Now, you're welcome to do C6H5 here. You're welcome to do that. Keep it consistent. But I know that a C6H5 is going to be a phenyl group. And then the second step, we're going to protonate it and just make this leftover anion into an OH. And let's see if it checks out with our spectroscopic data. Still, our 6H doublet still checks out. They're connected to 1 carbon, going to be a doublet. And our 1H multiplet checks out. Multiplet, no multiplet. And then our 1H doublet is still going to check out. We have our 1H here. You can also write this as CH. That's where that 1H is coming from. Our 1H coupling with that 1 hydrogen. A 1H singlet is always going to be indicative of an OH peak. And then we have a 5H, a monosubstituted benzene ring. All of it checks out. H2SO4 delta. This is another situation where semester 1 reactions will come in handy. If I have an alcohol and I were to react with H2SO4 and delta, I know I would have an E1-like elimination, right? And E1 is always going to be Zaitsev. So if I were to protonate the OH, make it H2O, H2O would pop off, creating carbocation, and there would be a double bond being formed. So I would have something like this, basically identical to what we have. Oops. Something like this, where this would become H2O plus, pop off, this proton would leave, and then that lone pair would form here. Something you learned in the first semester, right? And this should check out. Well, if I had an OH leaving, essentially, an OH and this OH and this H leaving, I'm basically removing molecular mass of 18. So if I were to take the 150 right here, minus the molecular mass of H2O, 18, I would get 132, which checks out. It is an elimination of a water. It's a dehydration reaction. And this checks out because we have a 6H singlet still. 6H, chemically equivalent, but they don't have any equivalent, or not equivalent, adjacent protons. A 1H singlet right here. No protons. And then we have a 3H, degree of freedom. I don't know where that might apply. And then a 2H right here. Our 2H and our 3H will add up to this, right? 3H, 2H, that's going to equal, oops, 3H, 2H, that's going to equal 5H. It's going to be our monosubstituted benzene ring. You might be thinking, well, how can you come to that kind of assumption? We didn't learn that at all. Well, like I told many students, and what my TO told me, is that whenever you do spectroscopic data, there's always 1 degree of freedom I have, right? If everything points to this one answer, and it's also based off of what you know, anything that doesn't point to it or points, well, yeah, just anything that doesn't point to it, it's okay. If one thing doesn't point to it, it's still Occam's razor. The most simple solution is the most probable solution, right? So if it's in the same aromatic region, 7.39, 7.60, this is still in the aromatic region, right? Aromatic. They still add up to 3H and 2H. my best bet is still they're all going to be aromatic hydrogens. It's going to be that 5H, right? It might not be all together, but hey, it might be because of the conjugated system with all of this, right? It's all part of that the 1 degree of freedom that I let myself have. Something that you guys should definitely take with you. Which of the following would react the fastest with a nucleophile? Well, in terms of reacting fastest with nucleophile, we're looking at both leaving group and steric hindrance. All right. Out of all of these, I know for a fact, excuse me. Oh, okay. We're chilling. We are chilling. OCH3, not only is it a bad leaving group, but it's electron donating and it would destabilize that carbonyl. I know this is going to be the least reactive. Now, between these, excuse me, an aldehyde, a ketone, and an anhydride. Out of these, anhydrides are going to be the most reactive. Why is that? Well, because you have the best leaving group right here, right? An aldehyde and a ketone, while you might have a activated or deactivated carbonyl compared to the anhydride, the anhydride is a very good leaving group. I don't know if you guys remember this from Gen Chem, but an acetate ion is a very, very good leaving group. And it is an extremely weak acid, weak base system. So it's a good leaving group. So this one's going to react faster with a nucleophile. If you guys remember, the reactivity to a nucleophile kind of follows that of an ANCO. And remember on my ANCO reactivity chart, you still have acyl chlorides, anhydrides, and then your aldehydes and your ketones, and every single other carboxylic acid derivative you've learned on that chart. That still applies here. Next question. Which of the following reacts fastest with a nucleophile? Oh my God, the same question again? Come on, you guys. Well, when we're talking about the reacting fastest with a nucleophile, we're probably going to be looking at these, steric hindrance, and electronic effect. So if I'm looking at all these are going to be ketones and aldehydes. I got an aldehyde, ketone, aldehyde, ketone. So out of all these, how do you differentiate between the two? Well, I would know that aldehydes are going to be more reactive than ketones straight up. So I can already cross out these. And then out of these two aldehydes, well, which one's most reactive to a nucleophile? Well, I have a CH2 and just a normal C. This one is going to be less sterically hindered because that branch is going to be farther away from that carbonyl. This branch is going to be a lot closer to that carbonyl. So I know that this one on the very left is going to be the most reactive. Which of the following compounds would react fastest with hydrolyzed NaOH? All right, when you have hydrolyzed NaOH, what does that mean? Well, that means which one is most likely going to be saponified, right? When you have a saponification, you're looking at that carbonyl carbon, because remember, saponification means that whatever ester group you have will leave, and then an OH will replace it. Granted, the H might be deprotonated, but you can hydrolyze it, put it in acidic solution, reprotonate it, but that's beyond the point. The best leaving group, the thing that leaves when you have an OH, which one's going to leave the best? Well, for this, we look at the same thing we look at acidity, right? Acidity, reactivity. Which one's going to have the most electron donating effect? I know for a fact that aniline is going to be the most electron donating. The most electron donating means that there's more electron density going into that carbonyl. It's going to be less electrophilic. OCH3, same thing. And then CH3 to a more minor amount. But a normal benzene, that's going to be the least electron donating compared to the rest. So this one would work. In the following reaction, methyl magnesium bromide is added until there isn't any more reaction. So it's in excess. and then it is acidified in a separate reaction. What is the end product? Well, if I have excess CH3 MgBr, right? If I have excess amounts, it's going to add to every carbonyl present, right? It's not some kind of weak reducing agent. Like remember, NaBH4 is a weak reducing agent. LiAlH4 is going to be a strong reducing agent. Grignard reactions are going to be strong reducing agents as well. So if we were to react to both in excess, it would be here. Because that first step would create something like this. Something like this. And then that third step, not third step, that second step would restore that proton. Because whatever methyl anion you have would attack to both carbonyls. Oh my God, bruh. All right. Now let's take a look at the mechanism. Now for the mechanism, complete the mechanism on the acid catalyzed hydrolysis of an ester. This should be pretty simple because it follows a lot of the mechanisms that we've been learning throughout class. The proton transfer is meant to activate whatever carbonyl you have, right? So if I have a carbonyl, let's say it were to do a proton transfer, it would attack here and do this. Like this. And we know that via resonance, this could form up here, and then that positive charge would be there, like a little bit of a door hinge maneuver. And basically, when you have an acid catalyst, whatever carbonyl you have makes that carbonyl more electrophilic. And if it's more electrophilic, that positive charge is here, then it's most likely going to be added upon by some kind of base, whatever nucleophile you have. And that base is most likely going to be water because it's going to be a hydrolysis reaction. So if you have a hydrolysis reaction, you would have an H2O, let's say an OH2, something like this. Always like this. OCH3. Yep. And then via proton transfer, I would remove one of these protons, and I would be left with an OH and an OH. And then if I were to do another proton transfer with that BH, I would essentially see the leaving group be protonated. Oops. If I were to eliminate it, I would have any of these OH groups donate here, and then that leaving group would leave, regenerate that ion OH, and then I would also have a leftover HOCH3, and then one final proton transfer where I have any kind of convenient base I have coming in, swooping that H right there. And this would be our final answer. All right. So the main things to note from this is that you start off the entire reaction with an acid catalyst. When you have your acid catalyst, you create that carbonyl carbon that is more electrophilic, and a lot of more things can add. And through your various intermediary proton transfers, you make the leaving group a better leaving group. If you acidify it, it's a lot more stable in your product solution. HOCH3 is a much better leaving group than OCH3. And then you use one final proton transfer to stabilize everything. Now let's take a look at some synthesis. For the roadmap, I have in a ketone, right? If I have a ketone, if I'm reacting it with CH3 MgBr, H3O+, Well, I know I have a electrophilic carbonyl right here. I know that CH3 minus, remember, Grignards are going to be alkyl anions. It's going to attack there. I know I'm going to have something like this. And this step right here, the H3O plus is going to go here. So I reduce that carbonyl into an alcohol. Now for product 2, I have H2SO4, delta, and H2PDon C. All right, here's a real tricky one. So for H2SO4, that first step is going to be an elimination reaction. I know that for every alcohol I have, if I use H2SO4, it's going to eliminate E1 like and thus eliminate eliminate Zaitsev wise. So if I were to eliminate this, it would form a double bond. And for this one, I have two methyl groups, so both are identical. So it doesn't matter which one I eliminate on. H2PD on C, I know it just reduces that double bond. So I knew I would have something like this. There's a cumene. Now for part 2, I have CH3, C, Cl. Something looks like this. It's going to be a Friedel-Crafts acylation. For the Friedel-Crafts acylation, again, it can either add both para, or not para, ortho, or para. But because of steric hindrance, out of the two, I would probably pick the para position. Right here. Then for product 4, NABH4, PBr3 pyridine, NHBr4 would probably reduce that acyl group into an OH. And then the Br would turn that OH in PBr3 would turn that OH into a Br. And then I have Mg dry ether, which would insert an ether between the carbon and the Br. And then I would react that with CO2 and then acidify it. So let's do the step 1 reaction. This one would be replaced with our CO2. And then with our third step right here, we would acidify it and just basically slap. Let me be more specific with that CO2. With that H3O plus, I would make that a carboxylic acid. Oh shit, final page. Oh fuck. All right, final page, you guys. You guys hype? It's already what time is it? 9:11. Oh, that's not a good number. That's not a good number. Oh, as Eneli Chapel once said, if I was a bad bitch, I'd want to fuck me too. Fuck! Come on, just get in there. Perfect. Perfect. Ta-da. Oh, that's so good. Oh, there it is. All right. That's Tuesday needs me. That's Tuesday needs me. Okay. Okay, fuck. Let's react this. All right, if I had a benzene ring and an amide. Mikhail, what are you looking at? It's okay. If I had a benzene ring, all right, and I had an amide is going to be weakly basic. But if I were to react it with NaOH, you might be thinking, well, why don't we have an aldol reaction? But for the aldol reaction, we don't have that happening because we don't have any alpha carbons, no hydrogens. That's not an alpha carbon. So the amide hydrogens are still protic, but they're not going to do any kind of aldol condensation with it. And if that's the case, NaOH, well, I have a protic group mixed in with a strong base. What's the most likely solution? That would most likely be an NH minus, and that phenyl group retained. No, it would not. No, it wouldn't.
Girl, that's saponification, baby. That gives a carboxylate.
I know. I'm a little, this is the last page. I'm pretty drunk right now. That is sponification. Give me 1 second. So you have the amine group, leaving group. It would leave with the NaOH coming in, attacking the carbonyl carbon. It would attach, become the OH, but because it's a basic solution, the H would pop off like this. Fuck. All right, I'm definitely not posting this. I'm definitely not posting this on YouTube. Great. Great, 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 great. All right. I have methanol and H3O plus. It's a weak base. All right, where does a weak base add? Carbonyl carbon or beta carbon? The answer is beta carbon. All right, you don't have to know the mechanism for it. You just need to know what it does. All right, I have ethanol. Oh my God. Speak of the devil, ethanol. Amen, brother. Amen. Oh, shit. Oh, ethanol HCl. If I have ethanol HCl, I have an ether group right here. It would just transesterify. Instead of a methyl group, it would just be an ET group. It would transesterify. All right. Now, here's a tricky one. Carboxylic acid and CH3NH2. For this one, you might be thinking, well, hey, I have a carboxylic acid derivatives. They have a very activated carbonyl carbon. So if I were to react it with CH3NH2, it should substitute, right? The answer is no. Carboxylic acids are going to be acidic. So if you react it with a base, like any kind of amine, literally any kind of amine, it would just rip off that proton and you would get a reaction that just pops off the proton from the benzoic acid. For this bottom left one, this is really easy, right? If you heat up
Wait, Patrick,
what?
tell them to put the salt. He took off. He took off. I got that wrong. Put the salt.
Bruh. He did that to you guys? That fucking sucks. Oh, that sucks. Here, let me pause recording real quick. Pause recording. All right, back to recording. Nothing happened. Nothing happened. When you heat up two carboxylic acid derivatives, not derivatives, if you heat up two carboxylic acids, they form an anhydride. For this one, it would be phthalic anhydride. There you go. Final column, you guys. If I have 2 servings of CH3 MgBr, well, the first serving would go ahead and up and replace this with whatever, it would replace this with whatever anion I had, CH3. But the second serving would go ahead and reduce this into CH3, COH, or actually be O, CH3 from the first serving, and another CH3. The thing is, for the second step, we basically protonate this part, making it OH. So have a tert-butyl alcohol. Now for the next one, let's say we were to have NaCCCH3. So I know this is going to be a C. What is it? CH3, some kind of salt. If I had a nucleophile base like this, if I were to react it with butanone, I would get something like this. And then I would do a proton transfer and make this into a hemiacetal. There you go. This is step 3 right here. All right. Now look, we have a methyl ethanoate reacting it with some kind of reducing agent. If I had a reducing agent, well, for the first serving, I would just, well, not even the first serving. I just know that whatever ether I have, it reduce it into a primary alcohol. It would get rid of this, turn this into a primary alcohol. So I'd have something like this. This would be CH2OH. Yeah. It reduces everything. For the ylide, hopefully you guys know that whatever compound you have connected to the phosphorus, you just paste onto the oxygen, kind of like what you would do for an aldol, where you would just paste it on. Bada bing, bada boom. Last one, CH3, 2, NH, trace H2, you create something like this. I think it would be, what is it? I think OH. If you had trace H or trace H plus, you would protonate the O. You would kick it out. You would create your imine. But the thing is, imines and enamines tautomerize between each other. The thing is, when you have a multi-substituted imine, the N-amine would be more stable. You would have a tautomerization. And thus, this form would be the most stable. Remember, imines and enamines are always in tautomerization with each other, kind of like enols and keto forms, right? The thing is, with this one, because it's di-substituted, when it has that double bond, it's going to hold that positive formal charge, and that's not favorable. And thus, that double charge, or that double bond is going to be favored. All right, I'm too fucking drunk for this shit. I'm going to end the recording.